we continue with our next speaker, which is kind of a follow-up of the previous one, because it's approximately the same topic, but this time about RISC-V and ARM. So please welcome Remy.
Hi, good afternoon, everyone. I hope you are done with the digestion. So yeah, this pretty much follows up or complements Karen's previous speech. But before I go into the details, obviously I work for a big company, so I have to put this disclaimer. And then if I speak too fast or if I don't articulate properly, please stop. Please stop me. With that said, who am I? I don't think it matters much. Well, this is my 16th time in FOSDEM, and it's only my first presentation, so bear with me. Having said that, I don't work in this field at all, so just a fun thing for me to do. So, some history. So, has anybody ever seen this? Outside the computer museum? Right. Yeah, so that's the Cray one. It's the first, indeed, it's the first vector processor. It's from the late or second half of the 70s. I wasn't even born back then. But point being, it's the first vector processor, and we all now finally, after almost 50 years, we're coming back to this kind of maybe coming back to this approach to calculations in computers. But for people my generation, this is more what we associate with SIMD before multimedia. So this is a pod, the first video game that actually used MMX, which MMX being the first SIMD extensions in the consumer business, in the consumer space, let's say. So as I said, MMX came in 1997. And that was 64-bit vectors, so you could compute over 64-bit at a time. Mind that back then computers was pretty much only 32 bits. And 2 years later came SSE, and many versions of SSE. SSE2, which is more popular in multimedia use cases, 2000. I'm not going to go through all the details of SSE because there's like a million versions. And AVX1 came in 2008. AVX2, which Karen mentioned, came in 2011. That was the first to have 256 bits vectors. Then AVX512, which was the topic of the previous presentation, officially came in 2013, but as Kieran mentioned, the only real proper CPUs were only out in 2017. On ARM side, the first SIMD was actually 32-bit only on ARM v6 in 2002. That doesn't really seem to make sense, but that's because it's basically calculating either 4 times 8 bits or 2 times 16 bits at a time. Then 128 bits came. There was no 64-bit SIMD on ARM. 28-bit came with ARM v7, so Cortex A8, usually called Neon. It's officially called Advanced SIMD in 2005, and on ARM v8, it's pretty much the same. Now it's not actually compatible, unlike on x86, where 64 and 32 are the same, but came with basically ARM v8 in 2012. It's also officially called Advanced SIMD, and it's also colloquially known as Neon. As for RISC-V, well, RISC-V is much more recent. There is no SIMD. Now the problem, and I've only summarized, this is only a short summary, there's way more extension, especially on the x86 side, is that every damn time you have to rewrite your assembly, and as the questions and answers in the previous talks and even the previous talk covered, this is kind of time consuming. So with that said, this was all fixed size SIMD. So what about variable length SIMD, which is what we will be talking about today? So how would you go about doing it? Well, simple way to do it is to just ask the CPU what is your vector size. And if you do RISC-V, this is how you do it. So control register read operation. The vector is called VLNB for vector length in bytes. And it will store in this case T0, whatever, it's one register, the number of bytes in a vector. And with that, you could then iterate. So if you want to know the number of elements, well, you have to do a left shift to compute the number of elements. So if you want to have 32-bit elements, you divide by 4, shift by 2 bits. Well, you could do it like that. And then you would write your main, you would take your C loop, you would convert it into assembler to operate on however many elements at a time. Then you would probably unroll to, like, if you have space in your vector bank, you'd probably unroll to eliminate or try to heat up the latency a little bit, because usually between instructions, if you operate only on one data set, you will have inter-instruction latencies which are going to hurt your performance. So you typically in multimedia unroll twice, so you will do work over two sets of vectors at the same time in parallel. And when you have done all of that, you will be working on however many, like say 32 items, 32 elements at a time. So you have to deal with edges because you might not have a multiple of 32 elements that you are dealing with. And that's fine, and that's one way to do it. In fact, last I checked, that's how Clang LLVM does the tree vectorization on RISC-V if you enable it. Even so, you have, it literally starts by reading the vector length and then deals with edges and unrolls twice. And if it manages to implement if you have enabled tree vectorization and you have enabled RISC-V vectors. But that's not really how you want to do it. But before we go to on how to actually do it, what vector lengths are we dealing with here? So obviously, well, as mentioned earlier, common values are 128 and 512 bits. So both ARM and RISC-V guarantees that even if you have a variable vector length, it's going to be at least 128 bits, and it's also going to be a power of 2 bits, which is kind of convenient for our calculations. So as far as I've seen, there are announcements for real hardware which would have 256 and 512 bits that you should be able to buy at some point in the near future. More crazy stuff. I've seen actually like designs also being announced with 1,000 bits. I don't know if they're going to store all those bits in the physical register bank, but it would be interesting if it happens. And I haven't seen theoretical designs at 4,000 bits. And I mean theoretical to the point that there is a schema. Theoretical in this case, I mean that there are actual schematics of how you could write a chip, and they have even simulation of the performance that the chip would get in certain algorithms. As to whether it's actually practically implementable in an existing industrial process, I don't know. I'm not a specialist in electronics, but that sounds a little bit questionable. So in theory, on the syntactic level, so in the instruction encoding level, you can have up to 2 power 16 bits, at least on RISC-V. I'm not sure about ARM actually. So how you actually do vector length, or are you supposed to do a variable vector length SIMD or vector processing as it's often called, although practically vector and SIMD are synonyms. Well, first you have to use predication, which is very highly prevalent in variable vector length scenarios. Now it's not a completely new concept. Kieran mentioned the K vectors, the K mask in AVX. So AVX also has predication, but in variable vector length, it's really essential because this is basically the programming model on variable vector length and loops is essentially built on predication. And that's true both for ARM and RISC-V. So a predicate is a vector of Boolean, so like the K mask in x86, it's called the P vector in ARM, and it's the mask vector in RISC-V. And as Kieran said, kind of repeating, but it just specifies which of the element in your vector, it specifies which ones you will be loading or modifying or storing out of a given instruction. So if it's a load instruction, which values you load from memory and overwrite into the register. If it's a store instruction, it's going to be the other way, which values in memory you're going to overwrite versus which ones are going to leave as they are. And if it's a calculation instruction, vector to vector, then it's going to tell you, it's going to affect which results are actually stored into the register versus which ones are just discarded. So on ARMv9 or SVE, one way you would typically do now your SVE loop instead of, say, your neon loop is you would start by counting down. You would initialize, say, extend to 0, and then you would, so here you have to imagine here that you have your actual neon or SVE loop. So you will check, you have this funny instruction which is actually called while LT or while LO, and you initialize the P0 vector in this case, which is one of the predicate register, to say that essentially you want to count how many elements you still have in your input data. So here we have we imagine that x0 is the number of elements we've been given to this function. X10 is a count of how far we've been, so it's our iterator. And we'll say, essentially what we'll say is as long as x10 is larger, as long as the number of elements we still have, sorry, as long as x0 is larger than the size of the vector that the CPU can handle, we'll just set the predicate to be clear. So we'll use the full size of the vector for our programming. And once the number of elements is more than 0, but strictly less than the vector size that the CPU can handle, then we'll start basically just ignoring the values at the end of the vector. So we'll have a bunch of 1s and then at the end a bunch of 0s. And this is how you abstract away and hide away the complexity of dealing with the edge in your loop. So essentially, by doing this, you don't care what is the actual capacity of. You don't actually need at any point to know how many elements you're dealing with in any iteration of your loop, because it's all hidden away by essentially the size of the vector and the size of the predicate are matched, so you don't actually care. And you also don't need to deal with edges because, well, even if there's 1 or 2 or 3 or 4 elements left over at the end, you can just deal with them in the last iteration, which of course will be a little bit less efficient than using the full size of the vector, but it's still much faster than having a separate edge, if only because you will not be stressing the instruction cache of the CPU. So that's predication. Now unrolling. If you thought about it, all that I just said with predication, it doesn't really work with unrolling. Because now you've counted down, you've set your predicate vector to count down how many elements you have still in your total count of elements. You can't unroll because now, you said, oh, I have 10 elements left, I'm going to use 10 elements in my vector, but if you have, it just doesn't work. Because if you had 1.5 vector left, you would want to have one predicate with all the bit set and another predicate with half of the bit set. This doesn't really work very well. And yes, now it's a bit of a hot take. Maybe I will never be ever again allowed to write FFmpeg code after this, but just don't unroll if you use variable vector lengths. Now there may be cases where you can unroll because it naturally have some kind of parallel in your design aspect in your algorithm, but the idea of vector processing is that we have higher latency and larger vectors, which in the end result in higher throughput, and we shouldn't need to unroll. I'm sure you will find actual designs, real hardware, real processor where it will be faster if you do unroll, and how much you need to unroll will depend on the design. And of course, if you are trying to squeeze the very last MIPS out of a given specific piece of hardware, then maybe you should unroll, but I think generally speaking, at least you shouldn't start by unrolling. And another interesting thing to keep in mind, which kind of already mentioned in the previous, kind of implied in the previous slide, is that you don't have alignment issues. So one common problem with SIMD instruction set is that the load and store instructions require over-aligned data, typically aligned on the side of the vector, which is very inconvenient when you're operating from C or C++ code, because it's usually your C++ allocator will only align on whatever the ABI specifies, which on ARM v8 would be 16 bytes for the stack and 8 bytes for the heap. So usually, well, at least both SVE and RISC-V vectors, they don't need, the alignment needed is only the alignment of the element, and it's not the alignment of it's not the size of the vector. So if you are operating on, say, 4 bytes pieces of data elements, then you only need your vectors to be aligned on 4 bytes, which is a very nice property for dealing, especially on the edge cases, and also you don't have to deal with, like, if you have one input that is aligned, that is perfectly aligned, and the output is not perfectly aligned, then you end up having this weird mismatch, and you end up having to deal with different edge cases. It's really a mess. With vector processing, you don't do that, so you don't actually have to worry about it. So with that, we've covered generalities. So how is it looking on ARM side? And then we'll see RISC-V side, because it's a bit weird if I thought like to put everything together, but then it becomes a huge mess. So it's going to be a bit repetitive because, of course, there's a lot of similarities. But so SVE came about like 5 years ago, a little bit more than 5 years ago. I think it was announced late 2016, if I recall correctly. It was pretty much useless for multimedia. It was explicitly meant for other things like, scientific applications or engineering modeling and this kind of stuff. HPC. And so nobody used it. At least nobody in this room used it. This was fixed with SVE2, which is sometimes called ARMv9 because it kind of comes with ARM version 9, but it's really called SVE2. Fix that issue. They realized that actually this is a good idea. This pattern programming model is also interesting for multimedia and crypto, which was also missing from SVE1. And so what they did is they just took which mnemonics were missing and added those, and it's pretty much the same mnemonics. You just add the operand, the predicate register. Famous last word is of course a little bit more complicated, but as I mentioned, you just use a while instruction, which will then provision your predicate, and you have to pick the element size so that of course this adds up correctly, and at the end you have a new set of branch conditions, so first element, last element, and so on and so forth. So the remaining elements will be determined by the predicate register, and then the predicate register will set the condition flag, and the while instruction will also subtract the count, the number of processed elements from your output register. And yeah, at this point, stop pretending that ARM is risk. How do you detect this stuff? So there's a processor macro. Otherwise, as usual on ARMv8, you have a bunch of privileged registers for the OS to look at. And then you have also on Linux, you have a bunch of flags in the auxiliary vector bit, so it's all classic. And otherwise, you're out of luck. Availability, so SVE said 2016, but didn't really work for us. SVE2 was specified in 2019, but so the real hardware came earlier last year. So Cortex X2 and all the other things from Dynamic IQ 110. Samsung Exynos 2200 and also Qualcomm. If you can see the references, they do have SVE. Unfortunately, it's only 128-bit vectors, and it's pretty damn expensive. But if you want to do it, you can find the hardware. So RISC-V, so different model.
Can I add?
Yeah.
There's also the Alibaba one, the Yitian.
Yeah, maybe. It's possible, yes.
It's only available in China, but it's available.
So on RISC-V, the predication is a little bit different. So they have separation between element count and the actual predicate. And so in practice in multimedia, maybe not in David, but usually you don't use the predicate at all. So we will instead just count the elements. And this is the instruction you always find at the beginning of the loop, which configures the vectors. So in this case, what we say is that we have a certain number of input elements. We want to get the number of output, the output operand is then the number of elements the CPU will deal with in the iteration. We then have to say the size of the element in bits, in this case, for instance, 16 bits. The group size, which is kind of free unrolling, it will automatically, if you set it to 2, it will use and you say you want to use vector 8, it will use vector 8 and vector 9 at the same time, for instance. And tail mode, we always set it to agnostic because we don't really care about tail mode, and mask mode, we also always set it to agnostic. There might be use cases where you need to do something else, which might be a little bit slower, but usually you don't. This is about how to deal with the stuff that is masked or with the elements that are at the end of the vector, which we don't care about. Usually you don't care about them, so you just tell the CPU you don't care about them. One cool thing about RISC-V, the floating point registers are separate from the vectors, unlike on ARM, so you have more registers available if you have hybrid calculations between scalar and vector side. But do mind the floating point convention, calling convention when this happens, otherwise you will screw up your register state and confuse your CPU. Big interesting stuff also about RISC-V, they have segmented load and store, which is similar to structured load and store in ARM, but they can do it up to 8 structures, whereas ARM is only up to 4. What is much more interesting perhaps is strided loads and store, where you can say, I have this register X, which contains a value, and that's going to be my stride. So for instance, with that, you can put the width of your video inside one register, and you can load all the pixels in a column in an instruction without having to then do weird shuffling and whatever.
Does that actually perform in practice?
I think that's going to depend on the design, but normally it should be in the data cache, which should be okay.
We're talking hypothetical architectures where it could be faster than the Gecko.
So I'll come to that. Yes, on the downside, you don't have transpose or zipping instructions, which should be annoying. So which is kind of the same. So you have to replace it with strides. So it's fine, and if you want to take every second element from one vector and so on. Feature detection. they have very, very detailed C preprocessor feature flags. I mean, you can download the slides if you're interested. On the other hand, on runtime detection is pretty crappy. You have to look up you have to trust the device tree node. You have to trust the bootloader to actually tell it to your OS correctly in the device tree data structure. And otherwise, there is a flag in the V bit, so the bit 21, because V is the 22nd letter in the alphabet, is a vector flag in the auxiliary vector for hardware capabilities on Linux. Availability, unfortunately, at this time, there is no hardware. Alibaba, T-Head has made hardware available, but it's implementing version 0.71 from about 18 months before the standardized specification, which is implemented by Clang and GCC. So you can kind of work with that, and it gives you some idea of the performance, but you're going to have to rewrite stuff because it's not completely bit compatible, so it's kind of annoying. I don't know when the stuff is going to happen. I'm pretty sure it's going to happen, but I would guess by the end of this year we are going to see hardware available. But also, I think one kind of not answering or dodging the previous question, but because we have so many different vendors on RISC-V, and I think there's more than I only listed 3 here, but I think there's other. There might be big difference between the performance characteristics of the different vendors. With their references.
Yes, I have just a few questions. One of them is, have you heard of the SVP64 project from LibreSoC yet? Which is a kind of a similar vector approach for PowerPC?
No, I haven't looked at PowerPC at all.
So another question that I had with my own SIMD programming work is, we often have applications that are inherently horizontal. For example, let's say you are writing a vectorized string search operation, or you're doing something like decoding JPEGs, where you have these 8x8 blocks, where you want to do some sort of cosine transform on them, and they have this fixed size, and depending on the vector size, you either have to break them up, or you maybe can process multiple of them at the same time. Is there an elegant way to solve this?
So, I've had this case. Yeah, so the question is, when you have a naturally fixed size data input block that you want to process at a time, how do you do this? Because then you actually want to have a fixed size vector, in effect, paraphrasing the question. So yeah, I've had this case with FFmpeg a couple of times. One way is to just check that the vector size of the CPU is big enough and just do one at a time. If you can, try to do n at a time, because it's always going to be a power of 2, so you should be able relatively easily to parallelize. I mean, obviously the ideal situation would be to parallelize. Where you will have a problem is if your data set is larger than the vector, then it's going to become complicated for you. On RISC-V, you can deal with this with the group multiplier, which will allow you to use multiple vectors as a single vector.
Okay. And the last question I have is, how do you realistically test vectorized kernels when the hardware you have only supports one vector length at most? So you have to probably use some sort of emulation to set up for this?
Most of the loops will not depend. So the question is, how do you test a different vector size for validation, I guess? Most of the loops don't really care about the vector size, because if you have the simple case where you follow the simple pattern, it doesn't really care what the vector size is, except for benchmarking, of course, then you have a problem. But otherwise, QEMU and Spike, at least for RISC-V, support any vector size that you give that, as long as it's a valid one from specification standpoint.
Do you realistically really test for that, or do you just say it's simple enough it won't be a problem?
I mean, personally, when I've had the situation where I had a fixed size input and I had to test with different vector sizes and I tested with different vector size, in most cases you don't actually care. I mean, then it's a matter of choice. How do you do your testing and how strict you want to be with the validation, I think. But,
Thank you.
So we have no online question.
First, a disclaimer: I'm related to the LibreSoC project because it's similar to RISC-V vectors, but not exactly the same. But they share a lot of the common ideas. You mentioned a very good point that CMD is not vector processing. In order, we tried to port some code from Neon to SV2. It was less than suboptimal, let's say. We had to revert back to the original C algorithm, and it made things much easier. Essentially, you forget about CMD, you go back to the original algorithm, then you try from there, and then expand.
So
convert
this is
to
kind of match with my personal experience. I think it depends. I mean, in most cases, I agree with you.
It
So the
depends,
question is
yes.
like, is it better to start from C or is it better to just
Yeah.
port Neon code to SVE code? I haven't actually done porting to SVE. I have ported from ARM to RISC-V, but yes, I think in many cases it's easier to start from C.
We had to rewrite completely our infrastructure, our basic logic, because here you have the head and tail. You have to deal with the edges of the buffers, and with SVE2 you cannot do that. You have to just
Yeah. So I mean, I agree. I think it also depends on the algorithm, but I agree. Yes.
Yeah.
Last question? No? Thank you, Rémi.